Right, good afternoon. Give me one moment. I bought my own laptop just to be annoying, and it takes a moment for it to switch over. So I'll just get that going there. All right. Let's just pull that up, put them in there. See, eventually it'll come on. So while I wait for that, I'll ask a question. Who here knows what raygun.io is before coming along? Okay, so we've got 5% of you. That's all right. Starting off, my name, as mentioned, is Daniel-Trask, and so we started Mindscape about 6 years ago, and we started out building development tools, particularly for .NET developers on the Microsoft stack. And about 18 months ago, 24 months ago, we decided that we wanted to build a product that we could target towards all software developers. And so we also wanted to do a couple of other things like provide a hosted service. And so we were looking around at what we could do there, and we decided that crash reporting seemed like an interesting sort of problem to try a hand at. So, you know, when your software crashes, like for example, there we go, Microsoft Word, you know, falls over when you've been working on a document and it says, we've sent this to Microsoft and, you know, it's going to get fixed, and you kind of know that's complete and utter bullcrap because Word never gets any better. We decided we should build a system like that for all software developers to be able to integrate, but they could actually action what was coming out of the end of it. And so we ended up picking the name Raygun because we wanted a cool name for the product, but we also didn't want to limit it to bug tracking. So as the service stands today, it reports crashes from a multitude of different programming languages, so .NET, Ruby on Rails. Yesterday we launched our Android provider, the Xamarin Stack, Node.js, JavaScript front-end errors, all that sort of stuff. So I'll just catch up to where we are. And so here, for example, is a screenshot from a dashboard for a given application. Hopefully that's clear enough. So you can see we've got a graph at the top that's showing how many errors a piece of software has. In this case, this is running on the Mindscape public website. So we put in a small piece of code into the site, takes only a few moments to get in there, and then whenever an error occurs, it gets sent to our service, which is hosted with Amazon. And over time we aggregate those up, and you'll see down the bottom we've uniquely grouped particular errors. So if any of you are sort of diligent software developers and you kind of go, all right, all software has bugs, so I'm going to put something into my code that sends me an email or something like that when something goes wrong, which is what I used to do back in the day. And you just start getting all of these emails, you know, and most of them are just complete and utter junk. So particularly for a website, you know, we get a lot of emails that are just web crawlers or, you know, things looking for exploits. So, you know, every single folder looking for a WP-admin WordPress sort of login or something like that. And you kind of get frustrated. And so you're getting all of these emails coming in, and you're slowly almost training yourself to pay no attention to them because most of them are not real problems. You're never going to fix them. And so we wanted to make sure that the system had certain states. So we wanted to take, for example, let's say any error where there was a 404 requesting /WP-admin. So for those of you who don't know, in WordPress land, that's the admin site, and usually what gets hit when somebody's trying to hack your site. We would take all of the instances of that error, collapse it down into one. So that would be one of the rows on the bottom there where you can see, for example, there was a file that's missing. It last occurred an hour ago and it's happened 21,985 times. Okay, so we'd bring those down, and then we'd let you set the state. So if it was a spurious error, you can say, I want to permanently ignore this, or you might deploy a fix for a genuine error and say it was resolved, and we'll notify you if something goes wrong. So we'll send you an email and say, hey, you know, you said you'd resolved this, but it's still broken. And I must admit, when we were working on the content for that email, I really wanted to put something real snarky in there about how people were shit coders, but didn't do it. So that's kind of the core dashboard for Raygun, and then you can obviously drill into a particular error to try and understand more about it. So when you get notified of a problem, whether it's, you know, in your mobile app or your website or whatever it is you've built, you can go in and you can see the trend for that particular error. You can go through the stack trace, you can attach custom data to it in your code, all of that sort of stuff that's in there. I don't want this to be a sales pitch on what Raygun is, so we'll move on to talking a little bit more about how we've gone about building this service. So we integrate with a whole lot of different products. We also consume data from a whole lot of different programming languages. So over time this has led to having to deal with more and more data, and so I wanted to talk about how we manage dealing with a lot of data. So from the sort of outside looking in, we host most of the system on Amazon's EC2 platform. We use that only because we've been with Amazon for hosting the Mindscape website for donkey's years, and we quite often get asked, why aren't you with Azure? You guys are known as a Microsoft shop, and it's just because we were already with Amazon. One bill is nicer than two. We use a bunch of different data storage bits that I'll sort of cover off on throughout the talk, but overall there's a lot of moving parts in our system. The front end is an ASP.NET web app, and we use Backbone.js and Marionette for that. And when we very first launched the product, our inflow was that we have a web service endpoint. So Raygun, as it stands at the moment, is a fully hosted service. You put a small piece of code into your product and it will send the error information and other logging information up to our endpoint. Then we would put it on a queue where we would use a product called Redis. Does anybody here not know what Redis is? Don't be ashamed. It's okay, cool. So Redis is a really cool sort of, you can think of it as a data structure server. So it typically runs all in memory, and it lets you have lists and queues and sets and linked lists and all sorts of cool stuff like that. It's super fast. Being fast is the sort of first sort of concern that the developer had with it, and so we run that on a box with a bunch of memory, and it has things like master-slave architecture and things like that for scaling it out. But we started off just using it for queuing. So we had one queue, and then we would have a worker process that would pop things off the queue, crunch the data, like for example finding out, do I have to create a new error group, or is this just being attached to an existing one? It also does things like say, oh, this user's integrated with HipChat, I'm going to send a message to their HipChat, I send them an email, all of that sort of stuff. And then we ultimately dumped all that data into a big MySQL bucket using Amazon's RDS platform. So that was what we had. We got to launch day. This is sort of, imagine it was about the 25th or so of February, and we thought, right, we're ready to go. We've built sort of a minimum viable product. We can throw this on the unsuspecting masses and see how they find it. And so I wanted to sort of just tell you a bit of a story. I try and get a picture of Will Smith into every presentation I do. About that sort of kickoff date. We all know the sort of saying in IT, that premature optimization is a bad thing and you ain't going to need to do that. So we thought we were pretty conservative. We thought, okay, we generate roughly this many errors. Let's assume that a client could send 10 times this many errors, and let's assume that we got, say, 100 people on the platform in the first week, and we added about 100 a week after that. Seemed like we'd sort of given ourselves enough headroom, which stands to reason, but that didn't hold, because basically about user number 2 or 3 was a top 10 Facebook game that was spamming our service to the tune of I think it was several million errors per hour, which meant that our architecture didn't really hold up that well. It didn't fall over. But we would have this problem where other users were saying, hey, like I'm testing this out and I threw an error and it's been 45 minutes and it hasn't shown up in your system, and we were like, that's because the system's cranking really hard dealing with this really badly written Facebook game. The guys even made it even worse eventually, because they decided that they wanted to just send sort of events, and so they would wrap up an exception and just set the message to the event, like, game loaded, game ended, and all this, and that just sent the volume of data through the roof. So we were getting at peak about 4 megabytes of JSON data per second from this single app streaming into our service, which was just kind of crazy, and we were sort of in the office going, oh crap, how do we make this sort of scale? And so we sort of were thinking, right, while we're going to review this, and we expected that we would continually have to review the architecture of the ray gun system as we continued to grow. I mean, we weren't planning to simply get, say, 300 users and then stop. We want to get thousands and thousands of users on here, and ideally some that are as large as that customer. So we went about looking about what could we do to make sure that certain things were met. Like, for example, high volume from one user didn't make it slower for another user, but we could handle lots of users with high volume. And the answer to it, like everything, a lot of things, queuing. We queue everything. Absolutely everything gets queued now. And so we adjusted our architecture from the one sort of queue that was sitting there to where we now set up a queue per application that a user registers with the system. And so in simple terms, this meant that we just had to adjust our worker so that it would effectively stripe the queues. Okay, so one of those queues could have 100 million errors sitting in it waiting to be processed. Another queue might have one, but the time between that worker being able to stripe through would stay the same. So you would still see your messages showing up in the system in, say, about 5 to 15 seconds is typically how long it takes. And the user who's sending so much data through, they'll take a bit longer, but frankly, if you're dealing with millions of messages now, you're probably not even going to notice that there was actually a bit of a delay in there because you've got bigger problems on your hands. We also went and made sure that the worker process could actually be scaled out across multiple boxes. So as we kind of go up, we can just continually add more boxes. The downside was the MySQL bucket on the end. That was a bit harder to deal with because, I'll jump back to the queuing thing, back about Redis. So as mentioned, we use Redis for that. I highly recommend everybody give it a little bit of a kick around. What we found was that Redis comes up a lot with a lot of the sort of big services that are out there that are trying to improve performance and scalability and things like that, and it's a little bit of a mind shift to get started with, but we used it just for the queues, and then now today we use Redis for so many different things within Raygun, for quickly slicing and dicing data, being able to do time filtering, time series related things. It's a really solid product, and it's free and open source. Anyway, the service was starting to go slow again because in the first month of launching, we ended up with 300 gigabytes of data stored in MySQL. Now, I'm a pretty opinionated guy, and I generally think MySQL is pretty crap to begin with, but RDS was a very nice service being offered by Amazon. It allowed us to do things like set up replication and backups with just a couple of clicks, and that was all really nice. But the database was starting to grind to a halt, and we were starting to get a lot of problems with locking as those workers were starting to throw more and more data into the database, and you were starting to scale it out. That caused a lot of contention. Also, 300 gigabytes in 1 month when you've only just launched, we'd all love the idea that we launch a product and we have 1 million users in month 1, but we didn't have 1 million users, we only had a handful. And that wasn't looking like it was going to scale well longer term. So we ended up introducing 2 new parts. So first off, we started sending the raw blobs of data. So when somebody sends a message into the Raygun service, it comes up to us as a JSON blob, and we would make sure that we persist that off to S3, and we've got a way of structuring that makes it manageable. This has the additional benefit that should we ever have sort of a catastrophic loss in, say, MySQL or Elasticsearch or whatever, we could effectively rebuild the entire data set by simply streaming the data back off S3 as though we were getting sent it originally. That allowed us to shift a lot of that data that was being stored within MySQL into just flat files on S3, and because we were hosting within the Amazon environment, the access speeds over S3 are actually really, really quick because you're already effectively in the same data center as your data. We also put Elasticsearch into the mix. So Elasticsearch is another open source product built on top of Lucene, and it's designed to allow you to sort of scale out a search cluster. And so we put that in because first and foremost, we had a lot of users saying, hey, I want to be able to find something that's in the database that I've sent up. And the other benefit for it is that it natively understands JSON as an input type. And so we would send it a JSON blob, and it can do cool things like automatically set up field mappings for each key value pair. So as mentioned, we allow you to send custom data attached to errors, for example, into Raygun. So if you were to do something like attach the currently logged in user's email address as a custom piece of data whenever you send an error if the user's logged in, you can now do a search with Raygun where you would just say, user : email address, and it will show you all of the errors that were impacting that user. And as we evolved, we wanted to be able to make it so that as we show, for example, impacted users, or say a server that's having a problem, you could click on that and actually see a list of all the exceptions that relate to those sort of properties, and then you can build that up more and more. So that allowed us to suck a whole lot of that data out of MySQL, plonk a lot of it onto S3 and a bunch more into Elasticsearch, because we knew there was no way we were going to be able to run like queries, for example, over that MySQL box that was already struggling. 14 minutes, cool. So this sort of summarises it. What we found though is that Elasticsearch is a very, very cool product, but we were running into some constraints where it just kept sort of falling over. So for example, the minimum suggested size for an Elasticsearch cluster is 3 nodes, and that allows for data replication and also sharing of the load for querying and indexing. And so we set this up on Amazon, and it just repeatedly, a single node would fall over and have a problem, and then it would try and bring it up, and another node would fall down, and we were kind of left scratching our head. We knew that we had a fair bit of data. At this point, we were somewhere around that 300 gigabyte mark. And we were rapidly trying to learn more and more about this, and Elasticsearch is written with Java. We have a lot of experience with .NET, but there were a couple of things that caught us off guard, which was the fact that Elasticsearch, you give it a particular amount of memory that it can use. It's very memory hungry, but if you ever spilled out of memory and it had to touch disk by swapping, Java would effectively thrash itself with the garbage collector and eventually kill the node and fall over. So that was not particularly great. So we went from fighting the one fire of dealing with a lot of data coming in with the fact that parts of our backend were starting to fall over. And I have been told when I've done the longer version of this presentation that it does sound like the service just falls over non-stop, but that's not true. The pieces that have sort of come off as we've been growing haven't actually generally affected performance, or we haven't lost any data, which is, knock on wood that I'm not standing here right now with half the service down. So we started looking around at hosting this, because we worked out that it was going to cost us at that time about $16 per customer to provide search, which seemed like per month, by the way, and that seemed like a lot of money just for a little search box. So we went hunting, and we came across this web host that is called DigitalOcean. Who here has heard of DigitalOcean? Cool. Okay, so a handful. So DigitalOcean is a sort of a startup, but they're quite a successful startup by some metrics, in that they have about 500,000 servers now. Sorry. And their key selling point is that they have solid-state disks, so SSD drives in all of their servers. And so we were finding we were having a lot of problems with the I/O throughput on Amazon. You can get SSD-backed Amazon instances, but they're kind of hard to come by, and they have to be quite large to begin with. And so this is an example. I'm sure most of you actually appreciate the difference between an SSD and a rusting disk hard drive, but this is the sort of throughput difference. We were managing about 20 megabytes per second read off EC2, and we can get about 550 megabytes per second reads off DigitalOcean, and about 300 megabytes per second writes. So we kind of worked on the theory that, okay, well, at least if it has to touch the disk's not going to be that slow. And there's other performance benefits, and there was actually quite a few other benefits to moving parts of our infrastructure to DigitalOcean, which was that they actually cost half as much, and they came with twice as much memory, and they had SSD disks. And so we managed to shift the cluster to having, I think it was about 48 gigs of memory for the 3 servers, SSD-backed IOPS, and we spent half as much, about $8 a customer. And then as we've grown, that price has come down and down and down, just because as we added more, and we haven't had to expand that cluster. I was sort of at the time expecting that we would have to add more servers to try and scale it up, but turns out it was just giving it that extra headroom, and the faster disks really helped. So that's good. So I recommend DigitalOcean for that stuff. They're pretty good, but we didn't shift all of the infrastructure onto DigitalOcean because they are relatively young. They don't offer quite as much stuff that, well, actually they don't offer a lot of stuff that Amazon offers. I mean, they've been in the cloud game for a very long time. We also wanted to try and keep the partly price down, but equally we knew that because we were building a sort of a DevOps tool, and there were certain things that we'd want to run, like tools that generally are built for Linux or Unix type environments, we wanted to have Linux servers, but we didn't necessarily want to sacrifice all the skills we had with C#. And so we've used Mono in quite a lot of parts of the Raygun system. The front-end website is still running on a Windows box though, but all of the back-end services are generally running on Linux machines, and that's been quite nice. We also set up load balancing, so we would run into occasional problems where if the API endpoint could go down, we suddenly weren't receiving any data. This is another really nice thing with Amazon's offering, was that you can set up an elastic load balancer, and then we just set up the API endpoint on multiple boxes, and it will effectively just round robin passing that data through. We just had the SSL cert sort of terminating on the load balancer and then just passing through, and that's worked really well as we've sort of received more and more data and more messages. I mean, we're at the point now where I think we process somewhere between about 5 and 10 million exception messages a day on a quiet day at the moment, so it's going up and up. Anyway, the load balancer, really nice and easy to set up. There is one little sort of hiccup to it, and that's that it only detects a box as being down when the box is unresponsive. So if your API endpoint is throwing 500 errors, for example, the load balancer still kind of goes, hey, cool, I'm getting replies. This box is just happy as Larry. I'll keep sending it messages. Haven't come up with a solution on how to deal with that quite yet. So this ended up with this sort of structure, where we now have the load balancer in front and multiple API endpoints all passing into multiple queues with multiple workers reading off of those and then passing off to those different data storage points, with Elasticsearch being a bunch of servers as well. So that's where we've ended up with, and that's scaling really well for us now. I don't think we're probably going to have to put in another server into our mix for probably until we maybe pass about 1,000 paying customers. By the point it's at 1,000 paying customers, though, we get to the stage where the price of a server is not really a big deal. And it's been quite impressive actually, just continually squeezing more and more performance out of boxes. And a couple of the slides that we showed at TechEd was that there is this common sort of mentality that developers are expensive, boxes are cheap, just keep putting in more boxes. And the truth is that stands when you're at the diminishing returns end of developers improving performance. Quite often we would run into things where somebody in the office could spend a day on something and improve the performance 50-fold. Well, that's great. If that saved us 50 boxes, that's a pretty big win for 1 day's worth of effort. And we keep finding more and more things like that to sort of keep squeezing performance out of the system. And that's led to tweets like this. Indy, who's a young lad down in Dunedin, he signed up with Raygun early on. He's actually just a high school kid who's built a parent-teacher interview system, and he's such a responsible developer that he wanted to keep an eye on how his system was going, but he's been a pretty good advocate for us. But when we see things like that, people saying that they're getting their error notifications before the user probably has even seen the error page come up, we know that the performance is kind of running as well as we could hope. So that kind of brings me to the end. I think I've managed to shave 5 minutes off there to catch us up a little bit more on time. If anybody has any questions, and also I'll be floating around for the rest of the day as well if you wanted to grab me afterwards.
Thanks very much, John Daniel. Very good stuff.
Thank you.
Some questions from the floor out there?
Thank you for good presentation. My question is, do you use your own system to troubleshoot implementation of your own system?
Parts of it, yes, but other parts have sort of SOS style systems in place, because if certain parts of the system go down, we would never obviously get told that it was down because of a circular failure. We use a range of monitoring tools to keep an eye on various parts of it. We've used a product called Munin to monitor all of the servers. Munin is but ugly, but it's effective. So it tells us, for example, load, memory, all of those sorts of things, and can highlight when there's appears to be trouble in places. We also do extensive logging around the place, and we have other notifications that'll run. We also have little sort of watchdog services that run on each of the boxes just to keep sure that things are running. And parts of the system, if there's an issue, can sort of be almost automatically resolved by those watchdogs, and other times they'll fall back to just letting us know that we need to fix things. The system is now at a point though where pretty much everything has redundancy built into it though. So if something does go down, it typically doesn't mean that we're actually offline or causing any trouble for our end users. Cool. Any other questions? Okay, cool. It's all good. Thanks for coming.